Hello everyone. In this sessions, we'll discuss buckling of column. So this is the content of this session. Introduction, pillar theory, effective length, types of column, limitations of pillar theory, and some example based on that pillar theory. Okay. So basically, columns are nothing but long and slender vertical structure members of uniform cross section which are subjected to some compressive load. Okay. Now there are lateral deflection of column under axial load that is known as a buckling. So when this suppose say when we are applying some load on vertical column, it will get buckled under two different direction. Okay, away from that axis and towards that axis. Now based upon this constraint, that buckling will going to happen. So the critical load for column with different end conditions will be derived using Euler theory. Now we'll discuss how that buckling will going to happen. There are some assumptions like suppose say if the column is made up of homogeneous, isotropic and perfect elastic material, then it will obey that Hooke's law. The column must have uniform cross section. The column is initially straight and the load is applied axially on that column. The weight of column is negligible. The column fails by only buckling. The direct compressive stresses are small compared to bending stresses, and length of column is large as compared to its lateral dimensions. So these are some assumptions which we can consider while deriving that Euler's equation. Now look at the buckling of the column. Now there are two scenarios. One is bending of column with convexity towards its initial position, that is considered as a positive, and second is concavity towards the initial position, that is considered as a negative. So based on the loading condition, based on the constraint, the column may get buckled in this two direction, either this direction or towards the origin or towards the axis of that particular column. Okay. Now the effective length is very important. That effective length we can consider based on its constraint position. Okay. Now to calculate that effective length, we have to first understand at which locations, at various position, at which positions it is constrained. So the effective length of a column with given end condition is defined as the length of equivalent column of same material and cross section with hinge end having same value of crippling load as that for given column. Now effective length is given by LE, and the Euler's equation for buckling of load, Euler buckling load is given by P is equal to pi square EI upon LE square, where its E is modulus of rigidity, I is area moment of inertia, then LE is equivalent length. Okay. Now look at the equation pi square EI upon LE square. So what we have initially, if you consider column with both the ends are hinged. Okay. So this is the initial position of column and this is the buckled position of that column. Okay. So when we consider column with both ends are hinged, then what will happen? Buckling will occur in this direction. Okay. So you can say P is equal to pi square EI upon LE square. At that time, we can write equivalent length is equal to L. That is LE is equal to L. So this is the equation of buckling of load, Euler buckling load, pi square EI upon L square. So this is the first case where when we are considering column with both the ends are hinged or pinned, then we have to apply L equivalent length is equal to actual length L. Then second equation, second conditions we have when one end is fixed and other is free. So this is free. So when we apply the load, it will be buckled like this. Okay. So what will happen? That crippling load will becomes pi square EI upon LE square. At that time, that equivalent length will become 2 times the actual length. Okay. So this is the deformation. So we can take deformation will be like this. When we apply this load, axial load on the column, it will be deformed like this or buckled like this. Okay. So the length will become twice of that actual length. Equivalent length is twice of that actual length. So that equation will become P is equal to pi square EI upon 2L bracket square. So it will become P is equal to pi square EI upon 4L square. That is the equation when one end is fixed and other is free. Now third type is when both the ends are fixed. So when both the ends are fixed, deformation will be like this. Okay. Now at that time, your equivalent length will become half of that actual length. So you can write pi square EI upon L by 2 bracket square. That is P is equal to 4 pi square EI upon L square. That is the equation for that buckling load. Then next, when one end is fixed and other is hinge or pin, at that time that equivalent length will become L by root 2. So this is the behavior of that column when one end is fixed and other is pin, and when we are apply axial load, it will be buckled like this. So at that time, you have to put that equivalent length equal to L by root 2. So we have P value 2 pi square EI upon L square. Okay. So these are the 4 cases for which we have to calculate buckling load. Okay. Now, then the Euler limitations of Euler's theory. So according to that Euler's theory, the crippling load for column with any end condition is given by P is equal to pi square EI upon L square. Now, that I value is your moment of inertia, which is AK square. So you can calculate radius of gyration for that particular structure of column. So that if you replace that value of I is equal to AK square, then you will get P value pi square E AK square upon LE square. So P is equal to pi square EA. We can take LE by K in one bracket. So LE by K is nothing but your radius of gyration. So that value will become stress is equal to force upon area. So you can write pi square E upon LE upon LE by K bracket square. So this is the equation which is crippling stress that we can determine if we have the value of equivalent length, radius of gyration, and modulus of elasticity. Okay. So this LE by K is nothing but your slenderness ratio. Okay. So that ratio we can calculate with the help of that stress and elasticity value. Okay. So this is the slenderness ratio, and this is for short column, this is for long column, and this is the value of stress which we can determine. Okay. So this is the curve. So we can define as the ratio of equivalent length of column to its minimum radius of gyration. That ratio is nothing but your slenderness ratio. Okay. I will solve some examples. We'll discuss some examples based upon this concept. Okay. So let's take this example. Suppose say a bar of length of 4 meter is used in simply supported beam and subjected to UDL of 30 kN per meter over the whole span. Now it deflects 15 mm at center. Determine the crippling load when it is used as a column with the following conditions. Now they have given 3 conditions. One is both the ends are pin joint. Second, one end is fixed, other is hinge, and third is both ends are fixed. Okay. So we can first we have to determine the value of elasticity and moment of inertia because that data is not available. So we can write delta is equal to, this is the equation when simply supported beam is subjected to UDL. So deflection is equal to 5 into W L raised to 4 upon 384 EI. That is the standard equation which we can use to calculate deflection. Now in this case, what we have deflection, 15 mm deflection is given. W is given, that is UDL is given 30 kN per meter. Length is also available, that is 4 meter. That length is given. Okay. And EI value we have to calculate. So if we put that value of deflection, load, UDL, and length, you will get E into I. That is elasticity into moment of inertia. So that value is 6.67 into 10 raised to 12 Newton mm square. Now we will take that condition. So when both the ends are pin joint, then we have equivalent length is equal to L. So we can calculate crippling load pi square EI upon L square. Put that value of E into I. Length is available, so we'll get that crippling load 4114.4 into 10 raised to 3. That is the crippling load when both the ends are pin joint. Now look at the second case. When one end is fixed and other is hinged. At that time, what is your equivalent length? Equivalent length will be L by root 2. So that equation will become P is equal to 2 pi square EI upon L square. So again, we can put that EI value, length value we can put. So we'll get that crippling load, which is 8228.8 into 10 raised to 3 Newton. Again, so one end is fixed. Okay. So third case, sorry, both the ends are fixed. At that time, L is equal to L by 2. So we can get that equation P is equal to pi square EI upon L by 2 bracket square, that is 4 pi square EI upon L square. So we have value of P 16457.6 into 10 raised to 3 Newton. So we'll stop for this session. These are the some cases which we have taken to calculate the buckling load of that particular column. Thank you.